Okay, see, before coming to this, let me also explain the previous merge sort using stack part. Okay, so I will just explain you that recursion only, that recursive function, how it will be executing. Okay, fine. So now presently what I will do is better, I will just take that code alone, the main, okay, void merge sort. Okay, so merge s o or the merge sort of, it will be taking three parameters, right? So one is your integer array ARR, second parameter is integer start, let me take it as S, and the third parameter is integer end E. By taking these three things as parameter, for the first thing that I need to do, I should declare a variable integer mid, and it should be equal to start plus end S plus E divided by 2. Then I will be checking whether if S is less than, like E, if S is less than E, then I will be calling the same function again, merge sort. And after calling merge sort, I will be passing first parameter ARR, second parameter yes, third parameter is mid. And this is first recursive call. Second recursive call is merge sort of. Okay, merge sort of ARR, comma, mid plus 1, comma, end, semicolon. Then the next one is merge. I'll call merge function. So merge function I'll call, and I'll pass ARR, I'll pass starting, I'll pass mid, I'll pass end also. That's it. So we'll close this if condition and also the function also. So we are going to check how this we are going to trace it out. Okay, so let me just start first of all by taking a very simple array. First of all, let me take an array size 8. I will take, okay, 1 2 3 4 5 6 and then 7 and 8. Let me take respective index 0 1 2 3 4 5 6 7. So now taking the 0 1 2 3 4 5 6 7, let me start picking out elements also. So let me pick out a few elements like 21 10 5 36 25 18 45 20. So this is a completely unsorted one, right? So now what I will do is I'll just start taking a stack. Okay, let me take a stack. Okay, fine. I'm just taking a stack now. Coming here to the stack memory, first thing what I will do is, what is the first call will be? First call will be merge sort of. Okay, see here, first activation area will be created. And this is actually activation area is just for merge sort. Okay, it is going to be for merge sort, a merge sort of, what is the parameter? First ARR is a parameter array, that's okay. But what about start and end? Start will be equal to 0 and end will be equal to last index, which is 7. That is the first, the function will be initially. I want to sort the entire array. So starting from 0 to 7, I need to sort. So 0, 7. So inside this, what will happen? You see, for every activation area, definitely this array can be accessed. Apart from this, that two main variables that will be created is start and end, where yes and e 7. Okay, fine. So which means when you just see here, let me just take line number 1, line number 2, line number 3, line number 4, line number 5. Okay, remember very well, we are creating something called as activation area. This box is what activation area. And when we will create this activation area is whenever a function is getting called, no matter it is recursive function or any function, but whenever a function is getting called, a new activation area will be created. Now initially from main function, this like merge sort of ARR, start, end was called. So that is the first activation area that I'm just creating. Now coming here, I will start executing line by line. First line number 1 I will start. Okay, line number 1. So I'll just start with line number 1. So what is line number 1 here? Line number 1 is mid is equal to start plus end divided by 2. What is S plus E here? S is 0, E is 7. When I add both of them, I will get 7. 7 divided by 2 has to be exactly 3.5. But since both are integer, we will get only the integer whole value, which is 3 we will get. So mid. So for mid also, we have found a value and we have just taken that also. For that also, memory block is created and value 3 is given. Okay, first line is over. What about the next line? Second line. We'll go with second line. What is second line? Checking whether S is less than E. Yes, I think S is 0, E is 7, S is definitely less than E. So second line is over. So then next thing is I need to go with third line because I'm entering into if block because of the condition is true. So entering into second line, third line. What is third line? Third line is a function call. So function call is there means I need to create one more activation area on top of the existing activation area. And this is also, this activation area is also for merge sort, but for a different, like parameter. Array parameter is same. What about the remaining parameter? Start and mid I'm taking. So what is start index? Start index is 0. What is end? Instead of end only, I passed mid, right? So what is the mid value? 3. So 3 will be taken. So merge sort of 0, 3 is taken here. So inside this, first of all, a memory block called as S is created and value 0 is posted. A memory block called as E is created and value 3 is posted here. Okay. Just 1 minute, students. Okay. So coming to this particular activation record, again, I will start from first line, which means the previous activation record or previous function, we have stopped at line number 3. Why we stopped at line number 3? Because line number 3, there was a function call. Once we see the function call, again, we go to first line and again we start. Okay. So again, coming to the next activation area, first line I will be executing. What is first line? Integer mid is equal to S plus E divided by 2. What is S plus E here? S is 0, E 0.5 exactly, but we'll take only the integer part. So midpoint will be equal to 1. Okay, so that is first line is over. What about second line? Second line is checking whether S is less than E. Yes, S is 0, E is 3. So I have definitely S is less than 3. So that's okay. Then after that, I need to go for third line because condition true. Condition true means I will enter into third line. What we have here, this is a function call first of all. So function call means what I need to do, I need to create one more activation record. And this activation record is also for merge sort. Okay, this activation area is also for merge sort. So what is the parameter? Parameter is start and mid. So take your previous activation area start index, which is 0. And what is the end mid index? Mid index is 1. So 0, 1 is taken as a parameter. And so I take away, like a memory block for S and I store 0 here. And I take a memory block for variable E and I store 1 inside here. And mid will be equal to, mid is equal to what is the midpoint? 0 plus 1 divided by 2. So 0 plus 1, start plus end, right? Start plus, so see, midpoint we will come later. First of all, S and E will be, like generated, right? While calling. Now we will just start with line number 1 for this particular activation area. That's line number 1 is integer mid is equal to S plus E divided by 2. So we will find mid is equal to S plus E, 0 plus 1, 1 divided by 2 is equal to 0 0.5, 0 0.5 only we will take that integer 0. Then we'll come to second line. Second line is checking whether your S is less than E. Yes, definitely the starting point here. S is 0, E is what? S is less than E, condition true. So when second line condition is true, we will enter into third line. Third line, what we have? We have a function call. Third line, what we have? We have function call. So third line, when we have a function call, what will happen? One more activation area will be created for that. And this is going to be merge sort. Okay, this is going to be merge sort of. Okay, this is going to be merge sort of. What is a parameter here? Third line, S comma mid. So starting index is 0. And what is mid? Mid is also 0. So I'm taking 0, 0. So here a memory block for S is created. 0 is the value. Memory block for E is created. Value is equal to 0. Now I just go and check first line. First line is finding the midpoint. So midpoint is mid is equal to 0 plus 0 divided by 2. Mid is also equal to 0. And then comes second line. Second line is checking whether start is less than end. No, start is not less than end. Both are equal. Start and 0 is not less than 0. So the condition is false. So when the second line condition is false, what happened? We need to come out of this if. Okay. So once we come out of the if, we see the close curly braces of the respective function. So I said when to create activation area. When to create activation activation area? Whenever a function is getting called, we need to create activation area. When to delete activation area? Two ways. One is either return statement is executed, you can delete, or otherwise if you have visited or if you are currently executing the closed curly braces of that respective function, entire function, a closed curly braces is executed, then that respective activation area have to be deleted. So which means here, once this closed curly braces is executed, the topmost activation area will be deleted. And once you delete this topmost activation area, you just return back to the immediate previous activation area you jump into. When you jump into the next immediate activation area, you go and check what was the last line number that we executed. We executed line number 3. Now we need to continue from where you left. So I have to go for line number 4. So what is line number 4? It is also again a function call. Okay, but different parameter, mid plus 1 comma e. So for that function call, definitely I will create one more activation record. And this is also for merge sort, the function merge sort. But parameter is mid plus 1 comma end. What is mid plus 1 here? Mid is 0, so 0 plus 1 is 1. Okay, 0 plus 1 is 1, and then comma end is also equal to 1. So mid plus 1 is 1 and end is 1. So merge sort of 1 comma 1 is a function call. So you create a memory block for S, you store 1, you create a memory block for E, and you store 1 here. Okay, so then what comes here, I will come to first line. First line is finding midpoint. What will be the midpoint here? Midpoint will be equal to 1 plus 1 divided by 2. So 1 plus 1, 2 divided by 2 is equal to 1. So mid is also equal to 1. Then what about second line? Second line is checking the condition whether S is less than E. But here the present S and E both are equal. They are not lesser. S is not less than E. So what happens automatically, because of that condition false, I see the closed curly braces of the entire function, for which the topmost activation area I'm just deleting. So once you eliminate the topmost activation area, then you come back to the next immediate activation record, where you see the last line executed, which is fourth line. So you need to continue from there, which is fifth line. What is fifth line? We are having fifth line also function call, but not recursive. It was just merge function where you are going to merge. What you are going to merge from start to mid and mid plus 1 to end. So what is start here? Start is 0, mid is 0, and end is 1. So from 0 comma 0 you take on one side. From 0 plus 1, 1 comma 1, you take 0 comma 0 separately, 1 comma 1 separately, and you merge. When you merge, what will happen is 0th index and 1th index, two elements will become sorted. So 0 comma 1, what happens? You take 0 comma 1 and merge, means only those big things will become sorted. So coming to 0 comma 1, it will become 1021. In the original array itself, it will become 1021. Okay, after that merge, fifth line merge operation is merge function is called. After that merge function is called, automatically this 0th index and 1th index will become sorted. And after fifth line, I need to come out of if block and execute the close curly braces of the function. So once that close curly braces is executed, automatically this topmost activation area will be deleted. This topmost activation area will be deleted. So once this topmost activation area is deleted, then you enter into the next activation record. And coming to this activation record, what was the last line executed? Last line executed was line number 3. So we should continue from there, which is line number 4. What is line number 4? Calling the same merge sort and passing mid plus 1 comma E. So one more activation area I will be creating for that. And this is going to be merge sort. Okay, this is going to be merge sort of, what is that? Mid plus 1 to end. What is mid here? 1. 1 plus 1 is 2, comma end is equal to 3. So merge sort of 2 comma 3 will be the function call. Okay, so then what I will do, I will just simply call, start with line number 1. But before that, a variable memory block for S will be created, value is 2. And memory block for E is also created, and the value is 3. And now, first line is finding the midpoint here. The midpoint is S plus E divided by 2. Which is starting and plus ending, which is 2 plus 3, 5. 5 divided by 2 is equal to 2 point something, which I can round it up to 2. So the midpoint is 2 here. Then let me come to second line. Second line is checking whether if S is less than E. S is 2 and E is 3. So yes, definitely both is lesser. Okay, both is definitely lesser. So S is definitely lesser than E. So when S is lesser than E, what we can do? We can proceed to third line. So what is third line? Third line is a function call, which is merge sort of ARR comma S comma mid. So by looking at that function call, definitely one more activation area I will be creating, where merge sort of, okay, merge sort of, what is the parameter? Start comma mid. So what is start here? Start here is 2. What is mid? Mid is actually 2. Okay, so then I will again create a memory block here. Yes, variable value 2 and E variable value 2. And now I'll start with first line, which is finding midpoint. Midpoint will be equal to 2 plus 2 divided by 2, which is 4 divided by 2 will be equal to 2. So midpoint also will be equal to 2. Then comes second line, checking whether S is less than E, but it is not. S is not less than E, condition false. So you come out of if block and the complete function gets over. So this activation area will be deleted. And once this activation area deleted, you enter into the previous activation area. Last line that is executed is third line. Last line that was executed is third line. So when last line that is executed is third line means what happens? Now I need to continue with fourth line. What is fourth line? What is fourth line? Fourth line is again calling the same function merge sort for mid plus 1 comma E. So one more activation area will be created, whereas merge sort function parameter is mid plus 1, which is 2 plus 1, 3 comma end point. End point is also 3. So merge sort of 3 comma 3. And whereas coming here, yes, and then I will just go with simply starting index is equal to 3, and then ending index is equal to 3. And what will be the mid index? What is going to be mid index? Mid index is equal to start plus end divided by 2. So start 3, end 3. So 3 plus 3, 6. 6 divided by 2 is equal to 3. Okay, now coming here to first line, midpoint is found. Then second line is we will compare S and E, whether S is less than E. But here starting point and ending point both are equal, they are not lesser. So if block is false, so you come out of if block and complete function is executed. So after the complete function is executed, then you delete the topmost activation area and you enter into the next activation area. Coming to this immediate next activation area, already up to fourth line it is done. Now what we will do, we will do it for fifth line. What is fifth line? Fifth line is merge operation between S to E. Like S to E means second index and third index, they will be merged separately. And second index, third index, they are already in sorted order, so they will be merged. Okay, then after you finish this particular process, okay, fifth line is over, right? Now what I will do is I will, after fifth line means after fifth line we will come out of if block and the close curly braces will be executed. Now I come to the next activation area where I have already completed up to fourth line. Now the next line is actually fifth line. Fifth line is merging process. So merging process between starting to mid, which is 0 to 1, is already become sorted. We know already 0 and 1 we sorted once, and 2 and 3 we merged and we made it also sorted. So 0 comma 1 is a separate sorted place, and 2 comma 3 is also separately a sorted array. Now we need to merge both of them. So when 0 comma 1 separately taken as array and 2 comma 3 separately taken as array, and if they are merged together, what will happen? The four arrays will become sorted. So what will happen is it will become 5 here. Then the next one will be 10, and then 21. 10 and 21 will be coming. Okay, see here, 10 and then 21. So 5, 10, 21, 36. So the first 4 elements becomes completely sorted. Now once after fifth line is executed, there is no more other lines to be executed. So automatically this activation area will be deleted. So when this activation area is deleted, you will enter into the next activation area, where that activation area will be like third line, right? You have to continue now from fourth line. What will be fourth line? Fourth line is merge sort of ARR comma mid plus 1 comma E, where one more activation area with S is equal to mid plus 1, which is 4. S will be 4 and E will be equal to 7. So already what you have done is from 0 comma 3 you took and you have already sorted. Now when you continue the same procedure, when you continue from 4 to 7 also, what will happen? Completely it will become sorted. So when both 4 commas, 0 comma 3 separately sorted and from 4 comma 7 separately sorted, what happens? This activation area finally I will be deleting once 4 to 7 it is sorted. Then you come here, and now coming to fifth line over here, what will happen? Merging process will happen between 0 to 3 and 4 to 7. So 0 to 3 is separately sorted order. Now 4 to 7 is separately sorted. When you merge both of them together, the entire array from 0 to 7 will become completely sorted. I see in between I skip a few activation records because I have done creating lot of activation area. I just said you the rule is very clear. Whenever you see a function call, you create activation area. Whenever you execute the closed curly braces, you delete the present activation area. That's simple, very simple. When you repeat like this similarly, you will be able to trace what is happening, which line will be executed in which way, which activation record, when it will be executed, what will be the impact of it. Everything you could understand simply if you follow this activation area creation deletion inside your stack memory. So is it everybody okay, like how this will be traced inside? Now, do you have idea of how this recursive functions will be executed? Is it clear for you? Is it now easy for you to understand? If any recursion is provided, will you be able to trace it easily? So any clarification, still any clarification or anything regarding like recursion, any question that you want to put forth, kindly just do it. 2 minutes, I'll just give you. Any clarification regarding this, you can put your question like in the chat. I think like now like instead of like going to like let us not take much time in the same thing. Let us go to like binary heap itself. Okay, so coming to binary heap. Okay, so binary heap. So coming to binary heap, as I said priorly, to understand binary heap, first of all, you should have a clear understanding of what is trees. You should have a clear understanding of what is trees. You have to have a clear understanding of what is binary trees. Okay, then you have to have a complete idea of not B trees, it is binary trees, because there is a separate tree called as B trees available. So this is binary tree, and it is going to be the next one is complete binary tree. You should have a clear knowledge of all these three things to get a good knowledge of what is binary heap. So can you just tell me what is a tree? When somebody asks you what is tree in data structure, okay, what is tree in data structure, I'm saying, okay, so what is tree in data structure, what would be the explanation that you give? See, it will be a little bit interactive. Okay, so when I ask, then I make a stop, I look at all your answers. If you post any answers, I look at all your explanation and continue. Don't think that in between the things are stuck, or like the voice is not audible. Like I'm just giving that pass in that. Okay, because like after every topic I give like a minimum of like 2 to 5 minutes of gap, because first you can take the time, and you can, first thing is you can just recall whatever things that I have said, because we will be little, I'm generally like little like quick in speaking every word, everything, so people says. So when I just fastly finish a particular concept, then I go with 2 to 5 minutes of gap, so that you can that point of time you can analyze, you can recall whatever things is done, and you can also relax and be prepared for the next topic. So I want to give always a gap between one topic to another topic, so that you relax and come to next topic, so you will have that grip on the second topic. Or once I suddenly start the second topic, what happens is people, like your mind will be on the previous topic, and things collapse. So that's why like for every one topic to another topic, between like I give some gap. Okay, so that would like mentally it will be helping. Okay, fine. So now like coming to trees. So when I ask somebody, ask you what is tree, what would be the definition? What would be the definition that you will be telling them? Post that in chat box, please. Okay, see here. So they're non-linear data structure. Trees are hierarchical data storage technique. Complete binary tree, a tree in which the nodes are filled only from left to right and top to bottom. Reason to use trees is we want to store info that naturally forms a hierarchy. Okay. Each element have only two child element is known as binary tree. Tree is a collection of nodes. Each nodes represent values. Hierarchical GS where each node has a reference to n number of child nodes. Nonlinear data structure which has a collection of objects called nodes. Collection of nodes. Hierarchical data structure consisting of nodes. Hierarchical struct. Tree is a collection of nodes. So like see, tree is a non-linear data structure, and it is a collection of node and edges, vertices and edges also you can say. Okay, and when you just look at this vertices and edges, whereas if you look at the graph and tree representation, the difference is, first thing is it is bidirectional. Graph is bidirectional. Either it can be like directional, a direct graph is also there, indirect graph is also there. But according to trees, there is no direction in terms of trees, and there is also no cycle. Same graph you take, undirected graphs if you take, and if there is an undirected graph without a cycle, then you can call it as a tree. There is an undirected graph without any cycle, then you can just simply call it as a tree, which means there will be no connected component in tree. Other than that, like graph and tree is, like most probably same. Only thing you can say is there will be no connected component in terms of trees. There will be no connected component. There will be no cycles. There is no direction. That's where, like tree differs. Okay, so we have a good knowledge of what is trees. Now, what is binary tree? Binary tree is if you take a complete tree structure, like for example, you take one node, then I take two nodes after this, then I take one here and one here, okay, one here. So when I take like a tree structure like this, okay, this is a node, okay, so this is an edge which is connecting two nodes. Okay, now every node, if you see here, there is a lot of relationships coming out of it. When you take a tree, there is a lot of relationships are there, like like family relationship you can compare over here. See, first of all, you take this is like consider this to be a person. This person is having two child. These two people called to be the child of this, because you look at this arrow mark, like arrow mark at this stick, from a person another two node is coming. Okay, so originating from this particular node, two other node is getting originated. So you can say this to be a parent node. You can call it as a parent node, and here these two people are called as child node because it is coming from like the upper node, right? So they are called as child node for this. Let me give a number for this node 1, 2, 3. So node number 2 is called as child node of 1th node, and node 1 is called as the parent node of 2nd node and 3rd node. So parent child relationship. Now when you just take this node, okay, and this node is having two child. So this node also can be a parent, but when it can be a parent, it can be a parent for node number 5 and node number 6, node number 4 and node number 5. And node number 4 will act as a child for this node, which is 2. 2 will act as a parent for 4 and 5, and 2 will act as a child for parent 1. Vice versa relationships are there. So this 4 and 5 will act as a child node for this parent node, which is node number 2. And the same node 4 and 5, it will act as a grandchild. It can be called as a grandchild for which node? It can be called as a grandchild for node number 1. Because if node 1 is a parent, node 4 is, like their child of child. Child's child. Okay, so you can call it as grandchild. So 4 and 5 will be a grandchild for node number 1. See, according to, node number 1, if I take it as a parent, okay, if I take node 1 as a parent, then node 2 and node 3 will be, node 2 and node 3 will be their child. Node 1, node 2 and node 3 will be a child. When you take 2 as a parent, okay, when you take node number 2 as a parent, then node number 4 and 5 will be acting as a child. When you take node 3 as a parent, okay, when you take node 3 as a parent, automatically node number 6 and node number 7. Node number 6 and node number 7 will be a child node. When you take node number 4, it cannot be called as a parent node because it does not have any child. Fourth node does not have any child. This fourth node can be called as a child of second node, and also this fourth node can be called as a grandchild of. It can be called as a grandchild of node number 1. And node 1 can be called as a grandparent for 4 and 5. 4, 5, 6, 7. For all this 4, 5, 6, 7, node number 1 can be called as grandparent. It will be called as a grandparent. Now, what is the relationship between node 2 and node 3? Can somebody tell me what is the relationship between node 2 and node 3? Node 2 and node 3, what is the relationship? I just spoke about the parent, child, grandparent, grandchild relationship. Now, what is the relationship between node 2 and node 3? Post it in the chat box. See, what you people do is list out all the relationships that is available here. And for every relationship, you give an example that this node is a parent of this node. This node is a child of this node. This node is a sibling of this node, a brother or node, or like sibling node. Like this, you write all the relationships as well as you write an example. You give an example for every relationship. You pick two node numbers and you give the relationship. Yes. Shall we take few time for do that, because we want to get very deep into binary heap. Let us just take few time, to have this basics. Okay. So write all the relationship. For every relationship, you give an example. You take two node and give an example and post it in the chat box. Okay. Just 3 minutes. I'll just wait for it. I'll look into it. Then we will proceed. After knowing the relationship better, then we will proceed with what is complete binary tree. After learning what is complete binary tree, then I will say what is binary heap is all about. Yes. Just 3 minutes. I'll just wait for you. Yes, go ahead. Yes. So yes. So what are the different relationships? Grandparent, grandchild, parent, child, sibling. For sibling, what is the best example? For sibling, the best example is 2 and 3 is sibling, 4 and 5 is sibling, 6 and 7 is sibling. And I hope you understand what is the sibling. Okay. Like the two node who have same parent. Okay. Two nodes having same parent can be called a sibling node. Okay. Then we have uncle or aunt node. Uncle, aunt, and nephew, nephew node will be there. So for example, like when you take 4 and 3, what is the relationship between 4 and 3? 4 and 3 if relationship. For 4, 3 can be called as uncle or aunt node. When you take 4 and 3 is uncle or aunt node, 4 can be called as nephew. Niece or nephew. Okay, niece or nephew. 4 will be called as niece or nephew. And 3, node number 3, niece or nephew, it will be called as, and node number 3, it is going to be either uncle or aunt node, you can call it as. Uncle or aunt node, you can call it as. This one, niece or nephew, you can call it as. So relationship between 4 and 3, 5 and 3, 6 and 2, 7 and 2, you can call it as niece or nephew, and uncle or aunt node. Okay, so these are the main relationships that you need to, first of all, you should have the clear understanding of, right? So now let us just come to what is complete binary tree. Okay, let us just come to what is complete binary tree. So can you just tell me what is complete binary tree is all about? What is complete binary? See, before that, what is full binary tree? Can somebody tell me what is full binary tree? Then we will go with the complete binary tree. So what is full binary tree is all about? What is full binary tree is all about? Is my voice is audible? My voice is audible?
Yes, sir.
Yeah, fine. Thank you. So now, so I was just asking you about complete binary tree and full binary tree. See, when we just come to full binary tree is any node if you take apart from the leaf node. This is a full binary tree. This you can call it as full binary tree because apart from the leaf node, every other node if you take exactly it will be having two child. Any parent or any node if you take, it will be having exactly two child. It will be having. Okay, fine. Then what about that? That's what full binary tree is all about. So any node, if you take, it will have two child, and except the leaf node. This node I'm just leaf node in the sense a node final level nodes are they are called as leaf nodes. Okay. Then coming to binary, complete binary tree. Complete binary tree is here. Every level will be completely filled. Like first level. See here, level I mean is generation. First generation. This is one level. This is second generation is one level, and this is one level. So this is level 1, level 2, level 3. So level wise, if you see every level will be completely filled. Completely filled means what is binary tree? Binary tree means maximum a node can have two child. Okay, so every level will be completely filled, but one liberation is that last level. When you come to last level, the elements can be filled from left to right, so it can be incomplete. Last level can be incomplete, but when you're filling the last level, you should be filling it from the left side. For example, I'll just first level filled, second level. This is a complete binary tree because first level is completely filled. Second level from the left you start filling it. Okay, so this is a complete binary tree. This is a complete binary tree. Okay, because only two level is available. Both the levels are completely filled. Now coming to third level, this is complete binary tree. This is a complete binary tree because last level we are filling it from left to right. But without this right side node, if a left side node is available, this is not complete binary tree. So last level when I'm filling, I should fill from left to right, and without missing any node in between, we should be filling. That's what like complete binary tree is all about. So every level should be filled except the last level. Coming to last level, you don't need the entire level to be filled, but the filling should happen from left to right without missing any intermediate nodes. That is the thing. So suppose if this node is also available, then I can call it as yes, this is complete binary tree. This is complete binary tree. Okay, fine. So do everybody is able to clearly understand what is this full binary tree and complete binary tree is all about? Now, shall we just go ahead with explaining what is binary heap is all about? Shall we? So everybody is clear with what is complete binary tree and full binary tree? Any clarification you require regarding that, please go ahead and ask. Okay, see, once again, let me repeat. Coming to full binary tree. Full binary, this is a full binary tree because any node, if you pick here, every node is exactly having two child. So when every node in a tree is exactly having two child, then we call it as full binary tree, except the last level, this one. Okay, except the last level, all the every other node if you pick, it should be exactly having two child. So if exactly two child is available for every node in a tree, then we call it as full binary tree. Is it full binary tree? First of all, clear? Is it full binary tree is clear? Okay. Now the next thing is complete binary tree. Okay, so complete binary tree. What is complete binary tree is, that's what I just was saying about levels. Do everybody understood about levels? First generation people belongs to level 1, that grandparent. Then their child, parent, they belongs to second level, second generation. And their childs, they belong to third generation. So generation wise, if you're just segregating it, every generation you can call it as level 1, level 2, level 3. Every level, it should be completely filled. Completely filled means every node should be having two child it should be having. For example, when I take first level maximum only one element can be available, right? First level, because from one grandparent only the entire hierarchy started. So first level only one element filled. Second element maximum two child. So two node will be maximum. Third level, each of this node which is in level 2, they will be having two child each. So this will be having 4 child. So 2 from here and 2 from here. So totally 4 child is over. So while filling the nodes, what you should be doing is every level should be filled completely. But last level, when you're coming, last level does not needs to be completely filled, but the filling should happen from left to right. The filling should happen from left to right, and you should not skip any node, and you should not go, because we are skipping the left child of this particular, see, node number 1, node number 2, node number 3, node number 4, node number 5 means left of node number 3 should be the next element, left of node number 3, but that's missing. You're missing one node and you're going to the next node. So you should have filled from left. So intermediate, if you're missing some element, it is not complete binary tree. Okay, but if the same node it is available like this, left side one node means this is complete. This is a complete binary tree. Even without this, it is a complete binary tree. Without this node 5 also, it is a complete binary tree. But after 4, after the left of 2, right of 2 should be available. Without right of 2, if left of 3 is available, it is not complete binary tree. So coming to last level, the filling should happen from left to right. No intermediate node should be missing. No intermediate node should be missing. So that's what I'm trying to say. This is what we call it as complete binary tree. Is this complete binary tree is clear for everybody? Is it complete binary tree is clear for everyone? Any clarification over this? Okay, fine. So yes, I think everybody is okay with this. Yes. See, for full binary tree, the exact definition, if you want to say, any child, if you take, either it should have 0 child or otherwise it should have exactly 2 child. No 1 child. Okay. Every node, if you pick, it will have either 2 child or 0 child. That's what in the leaf node I was just speaking, right? Leaf node, they will be having completely 0 child. So any node, if you pick in full binary tree, they should either have 2 child or otherwise they should be having 0 child. Okay. The exact explanation, if you see. Okay, so let us just like go ahead with what is binary heap. Complete binary tree is what complete like binary heap is all about. Okay, but in binary heap, what we will be doing is we'll be taking the like the tree structure of complete binary tree, and we will be converting that into arrays. Actually, binary heap is we are taking a tree structure and we are implementing a tree structure using arrays. We will be doing. But when you just come to this binary heap, B heap, okay, we can call it as B heap or binary heap. It has two different types, first of all. And the first type is going to be minimum binary heap, okay, min binary heap. Okay, it is going to be min binary heap. Okay, min binary heap. The other one is going to be max binary heap. Okay, min binary heap and max binary heap. So binary heap is divided into two different categories, where one is called as minimum binary heap, the other one is called as max binary heap. Okay, min binary heap and then max binary heap. So coming here to this minimum binary heap, okay, coming here to this minimum binary heap, what is minimum binary heap? When you take a complete binary tree, let us just take a complete binary tree for example. Okay. Yes. So this is a complete binary tree. Okay. So when I take a complete binary tree, what is minimum binary heap is any node if you pick. Okay, any set of parent child if you take, parent has to be always lesser and child has to be always greater, or at least the parent should be less than or equal to the child. It will not be greater. Any set of parent child. Like for example, here node number 1, node number 2, node number 3, node 4, node 5, node 6, node 7. If you take node 1, the value of node 1 should be less than or equal to the value of 2 and 3. The value of the node 2 value should be less than or equal to the value of 4, 5. The value of third node should be less than or equal to the value of sixth node and seventh node. This is what we were telling minimum binary heap. So any node if you pick, the parent should be lesser than or equal to the child node. When it is followed for every node, then it is called as minimum binary heap. What about maximum binary heap? It is just a contrast of it. So any parent child pair if you take, parent should be greater than or equal to child. Parent value should be greater than or equal to the child value. So if when you take 1th node, it should be greater than or equal to 2, 3. When you take second node, it should be greater than or equal to 4, 5. When you take third node, it should be greater than or equal to 6, 7. Okay, this is how this maximum binary heap, okay, will be going forward. Okay, this is how maximum binary. Okay, fine. So this is what minimum and maximum binary heap. So is it everybody clear with what is minimum and maximum binary heap? Okay. Scroll up a bit. Fine. 1 minute. Let me, yes. So generally, if you see here, complete binary tree is what minimum binary heap is all about. And we'll take this complete binary tree structure and we'll be implementing it as an array. We'll come to that, how we are going to convert this tree structure into array. But generally, binary heap is classified into minimum binary heap and maximum binary heap. Where minimum binary heap, if you take any node, if you take parent will be always lesser than or equal to the child node. Max is parent node will be having greater than or equal to value greater than or equal to child node. That's the only difference between minimum and maximum binary heap. Okay. First of all, let me take maximum binary heap. Let us take one example and let us construct a maximum binary heap. Okay. So let us just take an example. Example I'll pick is 21. I'll pick 10. The next one I'll just pick is let me pick 30. And next value let me pick is 15. Then let me pick 41. Then 25 and 32. 32. These are the elements that I'm picking. So 21, 10, 30, 15, 41, 25, 32. 7 elements. A total of 7 elements I'm picking. Okay, 21, 10. We need to take this element in the same order we need to take. We need to construct a maximum binary heap. So how we are going to? So shall we start? Shall we start with constructing this? Everybody good to go, right? Shall we start constructing this? Okay. So now coming here, first thing is I will create first node and I'll place 21 directly without any comparison, anything. I'll just directly take 21 and I will make it as a first node. Because nothing else to compare with, nothing to check whether complete binary tree is available or not, whether maximum binary heap proper, because only one element is available, so I can take it. Now from 10 only I will be checking for everything. So I'll take the next element 10. Where to insert 10? You have two positions, either on the left side of 21 or on the right side of 21. Where can we insert this 21? To the left of 21, where we can insert 10? To the right or to the left? Which one? Which place we will insert? Just tell me where we are going to insert this element 21. Either to the left or to the right. left. Why is it left? Because complete binary tree means the filling will happen from left to right. So that's why the element 10 should be inserted to the left. Okay. And also, while inserting, after inserting, what we need to do is we need to consider the element that we are inserting as a child, and we need to find its parent element, and we need to compare both of them. We are just looking for maximum binary heap. So maximum binary heap means the parent should be greater, child should be lesser. Is it right? Yes, it is followed properly. So I don't need to do anything. So already the parent is greater, child is lesser. Complete. It is also a complete binary tree. And also it is following the property of maximum binary heap. Now, what about the next element, 30? Where 30 has to be inserted to the right of 21, then only it will be a complete binary tree. So I will insert it to the right of 21. After inserting, this will become a child and this will become parent. So is it now parent is greater, child is lesser? No. Child is greater, parent is lesser. Is this a property of a maximum binary heap? Is this a property of a maximum binary heap? No. This is not the property of maximum binary heap. So what we need to do is, we need to make a swap between both of them. So this 21 and 30, they will be swapped. So 30 will reach here and 21 will come here. So once I make a swap, now if you look at it, complete binary tree it is, and also it is a maximum binary heap because 30 is lesser. See, 10 is lesser, 30 is greater, and 21 is lesser, 30. So if you take both the child is lesser comparing to parent. Okay, parent is greater, both the child so far is. So this is also following the property of max binary heap. So what is the procedure? If the child is greater and the parent is lesser, we need to make a swap between both of them. That's it. Now let us insert the next element, which is 15, where we need to insert 15 to the left of 10. Then only it will be a complete binary tree. After inserting 15, this is going to be considered as a child, and this will be acting as a parent. So child parent, when you compare, 15 is greater, child is greater, parent is lesser. So to make it as maximum binary heap, I need to make a swap between both of them, where now parent will become 15 and the child will become 10. And I will not stop here. I will not stop here because this 15, you have a choice. You have a chance because the inserted element, if it is 45, that 45 can also conflict with this root element 30, right? So we should not compare only with the, only we should not take the, the child element, compare it with parent. Now, after you find there is any violation and you are making a swap, now what you do is you take your parent as your new child and you find the parent node of that particular child. So now this 15 becomes child and its parent is here 30. Is it the child and parent is conflicting in terms of maximum binary heap? No. Parent is greater, child is smaller. Everything is followed properly. So in a certain place, if violation is not taking place, that you can stop. But until then, from bottom to top, you can keep on moving. For every child to become a pair, you can just keep on comparing. So now everything looks fine. What is the next element that I need to insert? 41. Where you need to insert? To the right of 15, I need to insert a node, create a node and insert 41. Now this I will consider to be child and I will find its parent. I'll compare both of them. Parent is lesser, child is greater. So it does not follow the, it definitely does not follow the maximum binary heap property. So I need to make a swap between both of them where 15 and 41 is swapped. 15 and 41. So 15 comes here and 41 goes there directly. So 15 and 41 is just completely swapped. Now I should not stop here. Now the parent, I need to take it as a child. Okay. So then this I have for this 41. Now what will be the parent? Here 30 will be the parent. Now child and parent, again we need to compare. So when you compare this child and parent, what happens? Child is greater, parent is lesser. Again violation taking place. So again we need to make a swap where in this node 30 will be coming and in the root node 41 will be appearing. Hereafter I cannot take, because if I just take this 41 as a child node, it will not have any parent because it is a root node. So once you reach root node, you can stop, or otherwise in between itself, if violation is not taking place, there it's also you can stop. So two places you can stop this process, violation checking process. Whereas if the child and parent is not any set of child and parent is not conflicting, you can stop there. Or otherwise, if you have reached the root node, okay, then you can just completely stop the process. Let me go to next insertion. What is the next element to be inserted? 25. So that 25 will be inserted to the left of 21. And after inserting, that will be considered as a child, and the 21 will be the parent. Parent is lesser, child is greater. So which is violating the property. So need to make a swap between 21 and 25, where this parent becomes 25 and the child will become 21. Then I will take this 25 as a new child and I'll find its parent 41. When I compare 25 and 41, parent is greater, child is lesser. No violation. No violation means I will just stop and I'll go to the next insertion. Okay, let me go for next insertion, which is 32 is the next element to be inserted. So when you want to insert this element 32, we will insert it to the right of 25 and taking it as a child and a parent 25. Parent lesser, child is greater. Definitely there is a conflict. So we need to make a swap between both of them. So 25 and 32 will be swapped, where 32 will become parent and 25 will become child. And then again, now parent, and now I will take this 32 as a new child, and my parent will be 41. When I compare this parent and child, parent is greater, child is okay. So check child and then parent. Okay, just check parent and then child. Parent is greater, child is lesser. So no violation. Stop. Now we just you look at the entire complete binary tree. Now any node if you pick here, parent is greater, child is lesser. 41, 30, 30, 32. Parent, child is lesser, parent greater. Take 30. 30 parent greater, child 10 and 15 lesser. Parent 32, child 21, 25 lesser. So any node if you pick, parent is greater, child is lesser. So it's completely following the property of maximum binary heap. First thing, to become a maximum binary heap, first of all, the tree structure that we are forming has to be complete binary tree. Second, we need to follow complete binary tree structure. Second thing is, we also have to make sure that any node if you pick, parent is higher. Okay, parent is greater and child is lesser. Okay, parent is bigger and child is lesser. let the sibling nodes to be, see, there is no restriction in terms of sibling node. Like 30 and 32, there is no restriction. 10, 15. So which one has to be greater, smaller? There is no rule for that. In terms of binary heap, the rule is defined for parent and child, not for siblings, not for any other relationships. So only for parent-child relationship. Always parent should be greater than or equal to child, no matter whatever the child or their siblings, like they are. So that doesn't matter. Okay. Sometimes, like sometimes what might occur is, like when you take this, like 30 or 25 and 21, this nodes will be comparatively greater than this node. That might also occur. But any parent child, if you take, they will definitely follow this parent greater than or equal to child. They will be following that properly. So we don't want to worry about any other uncle, aunt node, niece or nephew or siblings node, no matter what they are. Only thing, any parent child node, if you take, parent should be greater than or equal to child node. That is the only, like thing that we need to check. Okay, that's the only rule that we will be checking. Okay. If we look from leaves to, leaves to root, it looks like sorted. No, maybe for this example, it might look like that, fortunately, but not for all the cases. Like when you read it from the leaf to root, it will not be sorted. Just fortunately for this particular, like input, you're able to see like that. Okay, fine. So now, coming here, to this. Now, how we are going to take this and how we are going to convert this into array? It's the next question. But taking this and converting into array, before coming to that, let me give you one, like input. You just convert that into a binary heap and tell me the level wise order of that. Okay. So it is going to be the example that I'm going to put forth is 20, 56, 18, 29, 42, 8, then 12, okay, 20, okay. So, and one more element, 11. So when this is given, okay, this is a set of elements, input element is provided. So convert this into complete binary tree and post it in the chat box. Maximum binary heap. Student, sorry, due to like network issue, I just have been disconnected. I think now, you'll be able to hear me. I think I just gave you last, like 20, 56, 18, 29, 42, 8, 12, 11, all these elements I just gave you. And I asked you to form a complete, like a maximum binary heap. So the first element that we'll be creating is 20. Second element, 56, I will create it to the left of 20, I will create 56. Whereas 56, which is child, 20 is parent. So child greater parent smaller means it is not maximum binary heap. So we need to make a swap between 56 and 20. So 56 will become parent and 20 will become the root. Okay, I mean child. The next element is 18. 18 will be inserted to the right of 56. Okay. Now when you take this child parent, parent greater, child is smaller, so no issues. We'll go to next one, 29. So I will insert 29 to the left of 20, but 29 is greater, child is greater, parent is lesser. So I will have to make a swap between both of them where parent will become 29 and child will become 20. Then when you take this 29 and then 56 and compare, 56 is greater and 29 child is lesser. So there is no, like swapping over here. And next I have to go with, like the next value, which is 42. I will insert to the right of 29. Let me insert 42. And this 42 and 29, if I compare, child is greater, parent is lesser. So we need to make a swap. So 42, 29. Okay, so this is going to be 42 and this is going to be 29. It is going to be okay. Now when you take this 42 and compare it with 56, parent greater, child smaller, no issues, so we can stop. 8, then 18 left child is 8, so parent is greater, child is lesser, no issues. Then 12, parent is 18, child is 12. Okay, to the left of 20, parent is greater, child is lesser. So that's it completely. What is the element? 56, 42, 18, 20, 29, 8, 12, 11. This is the remaining elements, right? These are all, this is the order. So is it the same order that you also have got? So for 56, 56, left and right is 42 and 18. For 42, left and right is 20 and 29. For 18, the left and right child is 8 and 12. And for 20, the left child is 11. Perfect. Yes, I have given 8 elements. With 8 elements also, we could able to form complete binary tree. It's not like 7 or 15 we need to take. Any number of element is provided, complete binary tree is possible with that particular. Full binary tree only with certain numbering only you can form full binary tree. But complete binary tree, you don't have a restriction. With two node also complete binary tree is possible. 3 node also possible. 4 node is also possible. 5 node is also now possible. 6 node, 7 node is also possible. Okay, fine. Right? Is it everybody is clear with this? Now, understand how take level. So this will to 6. Okay, see, coming here, if I just simply want to convert this into an array, as I said, level wise we will take and store. First 41 will go to 0th index of array, 30 will go to 1th index of the array, 32 will go to 2nd index of the array, 10 will go to 3rd index, 15 will go to 4th index, 21 will go to 5th index, and 25 will go to 6th index. Like this, we have to take it an array. So in a normal tree, if you take parent child can be easily found, but how we are going to find a parent child when it becomes an array? So when you pick a certain ith index, like 2nd index or 4th index, certain ith index, and for that ith index, if you want to know where the parent will be, you just use the formula I minus 1 divided by 2. For any specific ith index, if you want to know where the parent will be, which index parent element will be available, use I minus 1 divided by 2. So you take 5. 5 minus 1, 4 divided by 2, 2. So parent of 21 is available in 2nd index. 6 minus 1, 5. 5 divided by 2 is 2.5. Round it off, you will get 2. So the parent of 6th index value is also available in 2nd index. So any ith index element parent, if you want to know, you just go to I minus 1 divided by 2 index. There you will find the parent. Similarly, for any ith index element, if you want to know the left child will be available in 2 multiplied by I plus 1 index. Right child will be available in 2 multiplied by I plus 2. So see here, 2 multiplied by 2, 4 plus 1, 5 is the left child index. 2 multiplied by 2, 4, 4 plus 2, 6 is the right side index. Similarly, on the left side, 1 multiplied by 2, 2 plus 1, third index is the left child. 1 multiplied by 2 plus 2. So 2 plus 2, 4 is the right child. Coming to 0. 0 multiplied by 2 is 0. 0 plus 1 is 1th index is left child. 0 multiplied by 2, 0 plus 2, right child. So for any ith index, if you want to know the left child by right child, you can use this 2 multiplied by I plus 1 and 2 multiplied by I plus 2. Is this everybody's clear with these two formulas? Suppose if the tree structure is converted to array, and I have written all the respective indices, level wise indices I have written for a specific ith index, if you want to know the parent index, you can use I minus 1 divided by 2. If you, for a certain ith index, if you want to know the left child and right child, we can use 2 multiplied by I plus 1 and 2 multiplied by I plus 2 we can use. So is this clear for everyone? Okay, so students, what we will do is we'll just go and take our lunch, come back afternoon, we will just, like implement all these things. Okay, next session. Okay, the next session we will implement all these things. Okay, okay, fine. So let us just like go for lunch. Thank you. Bye everyone. Bye. Thank you. Bye bye.